The last question on the most recent test was on volumes of revolution, and we did that last half term, but I just put it in there just to check that you know it, or so that you can work out that you need to do more work on it before your exam in January. Now before we get on to the question, just recap volumes of revolution. We're normally given a function, something like this, and I'm going to put both cases on here, and then we're given a bound region. So we might be given a region bound below the axis like R, below the curve, sorry, or you may also be given a region like this. Now, a lot of the confusion comes from what I just said when I said below the curve, because students think that integration is finding the area under the curve. Well, that's certainly true if the integration is respect to x. Now, if we just think about integration anyway, if this is the x-axis and this is the y-axis on both cases, if we were going to find the area R, so if we're just thinking about integration, area R is the integral, and if we're trying to find the area R, it's the area between the ordinates x1 and x2 and the curve, and it's the area between the curve and the axis, not the area under the axis. That's what I want you to think. It's the area bound by the curve and the x-axis when we're integrating with respect to x. So it's going to be y dx. And another way of writing it would be x, the integral of x1 of x2 of the function of x. Now, as we're integrating with respect to x, it's the area between the curve and the x-axis. I want to try and get away from the idea. I want you to try and get away from the idea, the area under the curve, because when you come to do this type of integration, typically you find it harder. Now, the same idea. If you're trying to find the area bound by this area R, it's going to be, let's call it R1. So area R1, that's area R, is now going to be the integral between y1 and y2 of x dy this time, or the integral of y1, y2 of the function of y dy. So when we want to find the area bound by the curve and the axis, we integrate with respect to, and the y-axis we integrate with respect to y, and when we want to find the area bound between the curve and the x-axis, we integrate with respect to x. So if we started off with some function y equals something on this one, we would have had to rearrange in terms of x. We would have had to make it a function of y rather than a function of x. Okay. So the same idea happens with volumes of revolution. If we are finding the area here and then rotating it around the x-axis, then we're integrating with respect to x. If we are finding the area R1 and then rotating around the y-axis, then we're integrating with respect to y. And as soon as you crack that, the better, because there are two types of formula that you can use depending on which case. Now, if you're going to do the volumes of revolution this time, so let's imagine we're going to rotate this around by 360 degrees or 4 right angles, so a complete rotation, we're going to do pi lots of the integral of between x1 and x2 of y with respect to x, because we're rotating around the x-axis, so it's dx. And what students get confused in is they think, well, that's got to be x there because we're going around the x-axis. Think more about what you're integrating respect to get the area, which you then rotate. And so that wasn't y, that's y squared. Okay? Or we could have written that as the pi lots of x1, x2, the function of x squared dx. And if we're going to do the volumes of revolution for this case, then we are going to rotate by 4 right angles around the y-axis. So in a similar fashion, it's going to be pi lots of the integral between y and y1 and y2 of x squared dy this time, because we're integrating around the y-axis, and we can also write that as pi lots of y1, y2 of the function of y squared dy. Okay, so it's squared because we're going to get the area. Now, if you don't understand why that works, then come and see me or look back in your books. But just try and imagine a whole series of very small discs with radius r, which you square and times by pi to get a circle. So we get a complete circle. So we've got a lot of circular discs basically, and the radius is increasing as the curve, in this case as the curve slopes up, each time the radius gets slightly bigger. So we're putting together a whole series of discs. But again, I can show you a much more accurate proof of that if you come and see me. So now we're going to use that idea to answer the question that you had on your test. So here it is. I didn't have a copy of the test with me, so I wrote it out again. We are going to find the volume when we rotate the area R around the x-axis through 4 right angles. And the area R is bound by the curve defined by y equals square root of e to the 2x plus 4, the x-axis, which is when y equals 0, the y-axis, x equals 0, and x equals 1.5. So we're going to rotate this area around the x-axis. So to find that area in the first place, we're going to have to integrate with respect to x, and we're rotating around the x-axis, so again it's got to be with respect to x. So we're going to integrate. So the volume is going to be, in this case, it's going to be the integral between pi lots of the integral between 0 and 1.5 of y squared dx. So if y is square root of e to the 2x plus 4, then y is equal to e to the 2x plus 4. So we're going to work out the volume is pi 0 to 1.5 of e to the 2x plus 4 with respect to x. Remember, we have squared this y, so we don't square it twice, so be careful that once you've squared it, you don't substitute it again and go, oh, I've got to square that. We've already squared it here. So we're going to get pi a half e to the 2x plus 4x between 0 and 1.5. Now if you didn't get that, then you need to go back and look at your integrating of exponential functions and your integrating of 4 from core 2 and your integrating of exponential functions from core 3, or come and see me, I can help you with that. So I'd like to see if you can finish it from there, leaving your answer in terms of pi and e. So pause your video. So here's my first step. I've substituted 1.5 in and I get a half e to the 3 plus 6. Now a lot of students miss off the next bit because they get so used to doing integration in core 2, and whenever you substitute 0 in, it just, you get 0. But remember, with an exponential function, e to the 0 is 1, so we don't make this bracket immediately 0 in your head. You've got to really think about it carefully, because that's actually going to be a half, because e to the 0 is 1, so you're going to have a half of 1 plus nothing. So that gives us a half of e to the 3 plus 6 minus a half, and then 6 take away a half gives 11 halves, positive 11 halves, which you then can factor out the half and then its units cubed. So that's the answer I would have given in the exam. Leave your answers in fractions, it's much easier to factor out. Okay, so the hard thing with volumes of revolution is to think, what are we doing? Are we integrating with respect to x or integrating with respect to y? If you're rotating around the x-axis, then you're integrating with respect to x, so it's going to be y squared, and if you're integrating around the y-axis, then you're integrating with respect to y, so it's going to be x squared. And one last thing to say here is that it's asked us to rotate it through 4 right angles, so 360 degrees. If they only wanted a half, 2 right angles, then you would have halved the pi. So if they only want a fraction of the 360 degree rotation, then that's a fraction of the pi that you need. So if they wanted 20% rotation, you do 20% of pi. Okay, so that's the only thing that you need to look out for. It's not always going to be pi. It's going to be depending on how much of the rotation you perform. So again, look for as many questions as you can if this is something you're finding difficult until you're comfortable, and if you need some more help on it, come and find me.